Welcome to a mini lecture about the theory of the colouring group. So this is what you can read about on pages 25 to 26 of the course notes. Here we go. So this is just a roundup of the theoretical results. And let's start in the top left corner with a reminder, what is the colouring group? So remember, the colouring group of a link L is the abelian group with the following presentation. First, its generators are things A, B, C, and so on, the arcs of a chosen diagram. We start by choosing a diagram, and then we take the group whose generators are the arcs, subject to some relations. Well, first of all, whenever we have a colouring equation for our diagram, we impose that as a relation. In other words, inside the group, we say that A plus B is equal to 2C, when A, B, and C are the labels of arcs at a crossing in the normal sense. And then one more relation, that our chosen arc A0, whichever one we choose, that's 0. And we've seen in previous videos how to work this out in practice, but here's some theory about it. So first of all, proposition. A link L can be coloured mod n, so back to the old notion of colourability, if and only if there's a non-zero homomorphism from the colouring group into the integers mod nz. So let's see why that should work. So let's do one implication. Let's show that if there is a non-zero homomorphism from the colouring group into the integers mod n, then we can colour L mod n. Let's check that. So let's start on the left with a non-zero homomorphism phi from the colouring group of L into the integers mod n. And from that we're going to extract a colouring of L, or rather of the diagram of L, the same diagram we used to define the colouring group. So here's what we do. We want to make a colouring. Well, our chosen arc, A0, we label it by, I wrote phi A0, I didn't mean that. We label it 0 in the normal way. So the chosen arc, we label it 0. Next, we label any other arc, A, by phi A. So remember, phi goes from the colouring group of L into Z over NZ. Each arc defines an element of the colouring group, so I can take that element of the colouring group and apply phi to it. So this phi A is an integer mod n, which I just think of as I choose any integer representing that integer mod n there, and that's what I label my other arcs, my non-chosen arcs, with. So I've labelled all the arcs of my diagram by an integer, and I need to check the colouring equation. And the way that works is, so suppose I've got arcs A, B, and C living at a crossing in the normal way. Well, then phi of A plus phi of B minus 2 phi of C, that's equal, inside the integers mod n, in other words, congruent mod n, let me write that, cong mod n, that's equal to, well, phi is a homomorphism. So instead of adding together phi A and phi B and subtracting 2 copies of phi C, that's the same as evaluating phi on A plus B minus 2C. So I'll just apply phi to all of the elements at once instead. And now, A plus B minus 2C inside the colouring group, that's 0. This is one of our relations. We said that this quantity here is 0. So phi of this is equal to phi of 0. And of course phi is a homomorphism, so that's 0. So we've checked that the colouring equations hold at every crossing. Finally, for this to be colouring, we needed phi to be non-zero. And it is, because the labelling, for this to be a colouring, we need the label not to be constant. Well, phi was non-zero, which means that phi of A, for some arc A, phi of A was non-zero, which means that we've labelled some other arc with something non-zero. So the labelling isn't constant. Okay, so that's the proof of how you go from one of these homomorphisms to a colouring, and I think you can see how to reverse that to go the other way. You can read the full proof in the notes. Okay, next, on the top right, theorem, which is the theorem you should have been waiting for. It says that the isomorphism class of the coloring group of a link L is a well-defined link invariant. I suppose I should say something about this phrase isomorphism class. You see, here's the problem. It can happen that two numbers can be equal. And these numbers, you could have computed them in lots of different ways. Maybe you had some theorem in a fancy course that says that this number is equal to this number. Well, then they can be the same. Now, suppose you constructed two different groups. It's almost never going to happen, even in good circumstances, that those two groups will be equal, right? However, it's much more likely that those two things can be isomorphic. In particular, when I defined for you the coloring group of a link, I had a chosen diagram in the background. Now, if I change that diagram, say by a Reidemeister move, I would like to say that I get the same group. But it won't be the same, they'll just be isomorphic. And they'll never be the same, they were written down differently. So I can never get equal. I can never get the coloring group as a well-defined link invariant, because it's always going to change by an isomorphism if I choose a different diagram. On the other hand, any two sets of choices are going to give isomorphic outcomes. So that's what I mean by the isomorphism class. The coloring group computed in any two ways, those two results will be isomorphic. Okay, and I won't say much about the proof. In fact, the notes don't say much about the proof. All I'll say is that the idea is that you use the same reasoning as you did when you proved that colorability mod n was a well-defined notion. And here's an important corollary. If the coloring group of L1 is not isomorphic to the coloring group of L2, then L1 and L2 are not equivalent. So this is something you can use when colorability can't tell your knots apart, when the determinant can't tell them apart, possibly the coloring group can. Okay, one final bit of theory. So let's, down here on the bottom right, let's start with the coloring matrix A. Or you could start with the Goeritz matrix if you wanted to. You can, if you wish, start with the Goeritz matrix. Then it's possible to find, it's possible to write your original matrix, it's possible to take your original matrix A, multiply it on the left by something with determinant 1, and on the right by something with determinant 1, so that the outcome is diagonal. So my label that said diagonal was in the wrong place. It should have said that D is diagonal. So let's rewrite that. There. D is diagonal. I can take my coloring matrix A, multiply it on the left by something integer matrix R with determinant 1, on the right by something else, integer matrix C with determinant 1, and the thing that pops out will be diagonal, and it will have this form here. Let's call the diagonal entries D1 up to DM. There. Then, in that case, the coloring matrix, the coloring group is isomorphic to this product of cyclic groups. All I do is, for each of these D's, I take the absolute value of D1 up to absolute value of DM, and I take the cyclic groups of those orders. Integers modulo absolute value of D1, blah blah blah, integers modulo absolute value of DM. And this is what we've been carrying out in the appendix A. So this is we find this using appendix A. Okay, theorem. The coloring group of L is infinite if and only if the determinant of L is 0. If the coloring group of L is finite, then the previous part told us that the determinant of L is non-zero, and in that case the determinant of L is the order of its coloring group. So we always know the order of the coloring group, it's the determinant. And in fact we can always get the determinant from the coloring group. If the coloring group is finite, the determinant is its order. If the coloring group is infinite, the determinant is 0. So what this is telling us is that the coloring group is more refined than the determinant. It may happen that two things have the same determinant, but maybe they have non-isomorphic coloring groups. And this is just because, how does this theorem work? It's just that you know that the determinant of D is the same as the determinant of A. In other words, the determinant of D is the determinant of our link. And then, well, let's look at the diagonal presentation. The determinant of D is the product of the DIs, which is the order of the colouring group based on this decomposition here. Okay, and then corollary, the determinant of L is a well-defined link invariant. So if you've been keeping close track of the theory in the course, you'll have noticed that we never proved the determinant is an invariant. You would have expected us probably to do something using Reidemeister moves. Well, we left it a while and then took this shortcut. The determinant is determined by the colouring group, and we know the colouring group is well defined. So we know the determinant is as well. Okay, so that's the end of this little trot through some theory.